G'day everyone. Welcome to another Toolbox Tech Talk this Sunday. Yay! I'll tell you what, Metro Melbourne's getting exciting. We can go out, we can do stuff, we can travel to regionals. It's great, and we can work. All of that's fantastic. Anyway, as you probably saw from the promo, today we're going to be talking all about Amendment 2 of 5033, 2014 edition. I know you're so excited, just stop the screaming. I can hear it from here. But first up, just want to thank all those people who come and watch my live streams. It's great to have some live audience out there. Those on YouTube, Facebook, on the Smart Energy Lab page, on the Storage and Solar Trainers page, sometimes a few on LinkedIn and even Periscope as well. So great. Now, I'm not the best at getting to the Q&A, but I'll try my best again today. Probably later, after I've done some of the presentation, I'll go and check to see what questions have popped up. But feel free just to add in the comments field any questions that you'd like to ask me during the live event. Couple of things, couple of announcements. I've been doing a lot of online training, actual courses. So I've been doing a 3-day electrical inspector course focusing just on 3 key standards, 5033, 4777 and the new battery standard 5139. I'll be running those again later this month. It'll be a early morning session, 7:30 Melbourne time for 4 hours each day, Tuesday through to Thursday. You can enroll on those courses on my enrolment website. Just to go to solarquip.com. I'll probably, if I remember, put a link in the description afterwards, but I forgot last week. Also, I'll be running a 5-day design and install course, which is really aimed at a broad audience of installers, designers, sales professionals, even enthusiasts for solar who want to know a lot more about the whole thing, how to put it all together. So it covers both on-grid and off-grid systems with solar and batteries. So those courses are coming up in early December. Yeah, and look, I'd just like to also thank my friend Chelsea, who bought me some new bling. Can you see it? I don't know. Where is it now? Seems that bling is the thing. So I've been getting some bling donations. And of course, a shout out to Solar Cutters, of course, for all of the great merch that they supplied me with. I just love the colours too, black and gold and red. Yeah, it's great. And I got the new T-shirt, the grey one. All right. Well, look, I think I can take my glasses off now. There we go. I don't have to be quite so cool, and start talking tech. So let's dive into it. Let's start with what is the problem when selecting a DC isolator to connect to a PV array. Now, it's a requirement, and it always has been in our PV array standard 5033 to have a means of disconnection. In Australia at the PV array, and in New Zealand optional at the PV array that you can use other means, and in Australia definitely at the PCE, at the inverter or charge controller, same in New Zealand. It may now be incorporated actually into the PCE, so have disconnection in the PCE, but Amendment 2 of 5033 covers this in some detail, what needs to be met. But one of the big problems is understanding how to choose the right product. And part of this is manufacturers of DC isolators catching up with the requirements of our amendment, Amendment 2, and giving you the information that you need. So let's start by looking at the problem. As always, I've got some hand-drawing pictures here, which is kind of my way of explaining stuff. So let me just jump over to that. So here we've got a grid connect inverter of yesteryear. Now I say of yesteryear because it's only got simple separation, and simple separation is where there is a isolating transformer between the DC side. I mean, there's a whole bunch of electronics in here I haven't drawn, but on the output of the power module there is a transformer that isolates the grid side from the PV array side. And therefore, the PV array will notionally be a floating PV array, unless it's functionally earthed, which really there's no good reason for it. No one would do it anymore. So PV arrays are floating with respect to earth. That means there's no pathway between the earth on the AC side, the MEN earth, and connection at the MEN to any part of the DC system. So in the good old days, and that was really only 10 years ago, when transformer or galvanically isolated inverters were the norm. But what we've seen is because of cost efficiency and weight, then being completely replaced with transformerless inverters. So you don't see these anymore. In fact, the very last one on the Australian market, the lovely Fronius Galvo, which I've got one here at the lab, was finally phased out. So big hurrah to the Fronius Galvo, but it was the last of the galvanically isolated inverters. So what we now have is this, a non-galvanically isolated, or to use the technical term, non-separated grid connect inverter. So non-separated means that when it's on and operating, there is effectively a path straight through the inverter. It alternates as it's switching, but effectively there's a path straight through the inverter that is providing a connection between the DC side and the AC side. And therefore the only isolation we have is the electronics inside this unit, which aren't foolproof. So there can be a fault condition whereby we may get a reference on the AC side providing a pathway back to the DC. Now, when does this happen? When does this become a problem? Well, let's introduce a fault. So if we've got a fault here, we've got a pinched cable, and so we've got an accidental earth on the array. So this accidental earth here could be a faulty module. If you happen to be in Springfield, Brisbane recently, you've probably seen a lot of them after that amazing hailstorm that just obliterated whole suburbs of solar panels. But equally, just a pinched cable, or the popular possum chewed on my cable problem, causing the equal potential bonding earth on the array frame or the array to connect to the DC side. Now, when that happens with a transformerless inverter, what you're going to see is a fault current straight away flowing like this through the positive leg, through the transformer, down the street, and all the way back. And so that's the fault path. And you'll note that in terms of this device here, which is our DC isolator, the DC isolator is now only switching one conductor. Only the positive conductor is interrupting this current. And so this is a problem. That means under these fault conditions, we need a way with only one conductor being interrupted that it will adequately do this. So the voltage rating and the current rating of one conductor path through the DC isolator under fault conditions needs to be suitably rated. And that's introduced a new term, which I'll come to in a minute, the I make, I break ratings for DC isolators. But anyway, let's go on and look at some technical terminology used to describe a rating of a isolator. So there's a bunch of things you need to determine when selecting a DC isolator. You need to actually know what you're connecting it to. Are you connecting it to something with it's separated, so it's got galvanic isolation, unlikely these days if it's new, or is it non-separated, a transformerless inverter, or even a maximum power point tracking charge controller with a functional earth on the battery side that still would provide a possible earth loop through the PCE. That's pretty unusual though. We also need to calculate what the open circuit voltage corrected for the lowest expected operating temperature of the PV array. And I'll go into a bit more detail on that in a second, explaining how we do that. The PV array short circuit current, we require a multiplying factor of 1.25 times. That comes from 5033 table 4.2. So this is our minimum current carrying capacity of our PV array cable, and therefore the possible higher than expected fault current. I mean, the reasoning behind this, by the way, is the ISC of a panel is only at standard test conditions, which is 1,000 watts per square meter. It is possible to get higher irradiance than 1,000 watts per square meter, and that can lead to higher currents. In fact, irradiance and current are almost directly proportional to each other. So if you were to get 1,100 watts per square meter, you'd get 10% more current. So we put a good healthy safety margin there on the minimum current carrying capacity of the cable. We need to know the location of the isolator. Now this is a new thing too. We've come up with 3 possible locations, which I'll mention in a minute, and that will determine the temperature derating of the isolator based on those locations. Now jumping over to AS 60947.3 2018 edition, this is where it does get pretty technical, and we need to know these terminologies because these symbols will be used in the manual or the data sheet for the DC isolator, so you need to understand what they're doing. So we've got U with a little subscript E, so U for voltage, the rated operational voltage of the isolator. That's pretty straightforward. IE is the rated operational currents of the DC isolator. That's pretty straightforward. But then we've got these new ones, and these actually come straight out of the test, but they're now required in the selection process for our switch disconnector. So we've got a ITH, which is conventional free air thermal current, i.e. it's not enclosed. Then we've got ITHE, which is conventional enclosed thermal current, so we've now got the isolator enclosed. And then we've got these two, I make, I break, which is really fault currents. What's the ability to interrupt a fault current? And the ratings for those are often a very small number of operations, not the usual thousands of operations. So these ones weren't commonly referred to. In fact, they were in the test. So products tested to 60947.3 already had these tests done on them, but they weren't often published on the data sheet of the switch disconnector or DC isolator. But we now need to have those, so that's pretty important. I was looking at some data sheets from very good quality products from yesteryear, and they're probably still perfectly suitable, but the old data sheets just don't mention those. So let's go through a few other things. The utilisation category of the isolator needs to be DC PV2. Now this is kind of an upgrade from the old DC 21B utilisation category, which was for only moderate overloads. DC PV2 now is for connection and disconnection PV circuits with significant overcurrents in both directions. Now we've actually had this requirement for non-polarisation of disconnectors and circuit breakers used on the PV array side for a long time, so that's nothing new. So this both directions just means non-polarized. We've added the new ingress protection or IP rating minimum, so a minimum of IP56 no water. Now this NW is kind of an Australian New Zealand thing we've thrown in there. Basically it means that the enclosure must meet the test for IPX6. Now 6 is spraying water from any direction, but additional to that test, it must still have no water ingress, so not a droplet, not a bit of moisture even. So that's a high level of moisture barrier. So IP56 minimum, you can be higher than that, it could be 66 for instance, but that last digit has to be a 6 with NW following. Now lastly we're getting to these different thermal ratings. Now we came up with 3 categories. Rather than, as you previously might have had to do, is determine what the operating temperature of the isolator or disconnector was, now we're telling you you've got 3 choices. Is it indoors? And therefore you have to use the 40 degree ambient rating for current for the isolator. Is it outdoors but fully shaded? Now that would be like a veranda, or a carport, fully shaded, then you can use the 40 degree ambient for fully shaded. Is it outdoors but in it's maybe an enclosure or with a shroud that receives direct sunlight, you use the 60 degree ambient rating for the product in those situations. So we've got these 3 thermal effects that we need to consider. So the manufacturer needs to be able to provide you with those thermal ratings in terms of current ratings at those under those conditions. All right, let's go to one more little explainer here. Now I did mention that you need to be able to calculate the maximum open circuit voltage of the PV array. This is nothing new. 5033 has always required this. In fact, 5033, ASNZ is 5033 is always referred to VOC as VOC max. That's always been the case. And VOC max is at the coldest expected operating temperature. Now this is how you could calculate it using a data sheet for a module. So here I've used the LG Neon R module, the 365 watt I think it is, and it has a really impressive temperature coefficient of minus 0.24% per degree Celsius. That means for every 0.24 degrees of temperature rise above standard test conditions, which standard test conditions is 25 degrees Celsius, so every cell temperature as it goes up from 25 degrees Celsius, it will then increase the voltage by 0.24%. But it's a linear gradient, so it goes in the other direction as well. So as you lower the temperature of the cells, they will increase in voltage. And so I've chosen -5. I live here in Mount Tulibawong. In the Yarra Valley, we get snow in winter. It does get down to minus something, -2 or 3. So I've chosen -5 just to be safe. And therefore, I'm actually minus 30 degrees below test conditions. And therefore, when I calculate the voltage increase, it's 7.2%. It's really quite significant. So my modules go from 42.8 volts at standard test conditions to 45.9. Now we're going to do a full worked example here. But before I go to that, there are actually 2 other strategies. This is the fully worked way of doing it. But what you can do is actually use table 4.1 from 5033. It gives you a multiplying factor for 5-degree temperature ranges. So you might be in the -1 to -5 range. And so your multiplying factor might be I'm trying to remember what it is, 1.12, I think. So you can just use that table. The third methodology that's permitted is if the manufacturer actually tells you at a certain temperature what the VOC will be. I've never seen it except for test conditions, so that's probably never going to happen. And here we go. So here's a worked example, how we go about doing this calculation. So I've chosen the LG Neon R modules, and it's the 365 watt module. I've looked up on the datasheet, found its VOC at standard test conditions, its ISC at standard test conditions. And we're going to build a 13 module series string of panels, which is about 4.7 kilowatts roughly. And we're going to see if the isolator that I'm going to bring up on screen in a minute is suitable. So first we do the calculation for the coldest expected operating temperature. I've chosen -5. So we're going to sneak in at under 600 volts. Woohoo! See, domestic installation. So in Australia and New Zealand, you must be below 600 volts at the coldest expected operating temperature. So we just sneak in there at 597. It'd be great to see that 600 volt limit change, by the way. The PV array minimum current rating, current carrying capacity, is the 1.2 multiplier on the ISC. So the ISC is for one module and there's 13 in series. So it's still 10.8 amps times 1.25 gives us a rating of 13.5. So our isolator needs to be able to interrupt 13.5 amps at 597 volts. All right. So let's look at where we're going to put it. The DC isolator in this case, in this example, is going to be installed outside in direct sunlight. I deliberately sort of chose the toughest location. So now I kind of need to switch over and bring up a picture of that isolator. So let's just bring that up. So go. Here we go. A ZJBeny. Now, ZJBeny, very popular brand, certainly in Australia, of DC isolator. And hats off to ZJBeny because they've really done a great job of their data sheet. So, yeah, congratulations to the engineers, no doubt, who spent some time making sure that they had all the information we needed for a compliant DC isolator, or at least to know that we could meet the compliance requirements. So, if I just get my mouse up there. It's IP66. Now, we'll see that the no water bit comes in further on when they specify that. It's DC utilisation category DC PV2, that's great, as well as the old DC21B, and gives some maximum currents and voltages there for those utilisation categories. Incidentally, utilisation is about how many times you can operate it, as well as what current. It comes in a 4-pole device, but you could actually use 2 poles on one string and 2 poles on another. But I think that may be rather limited, and we'll look at that in a second. And it also has a built-in earthing terminal, which can be handy for PV array earthing. There's a picture of the unit. So I'll just scroll down a little bit and bring up a bit more data here. So this is the stuff that we're really interested in. Now, one of the challenges, and gee, I probably need to tell the story here actually. I'm just going to cut to me for the story time. So everyone comfortable sitting on your cushions there. Time for a story from Glenn. Yeah, this is back about when the 5033 came out, I think it was the 2012 edition. I was presenting to an audience at Osgrid of about 300 installers on the new 5033 and getting people's heads around it. And there was quite a lot of technical detail that was being mentioned. And there was this guy sitting in the front row, and he had a suit on, so he didn't look like your average installer. Turned out he was an electrical engineer. You can always tell them. They're the ones wearing the suits. They're the ones earning the big dollars. Anyway, during the break, he came up to me and said, look, Glenn, politely, I'm surprised that you expect electricians to do all these calculations. This is really engineering. Why are we selling systems that require so much engineering to be done just to make sure that they're safe? They should be pre-engineered as a package. And I said, oh, look, I'm afraid that's not the case. In fact, you underestimate how smart our electricians really are, and they can do this stuff with training. And that's really why training's so important with PV. So whether you're a designer, an installer, or a sales professional, knowing this stuff is really important. And so PV systems are really pushing the boundaries in terms of some new tech. So hence I'm doing this Toolbox Tech Talk just about DC isolators. Anyway, that was the story time. Let's go back to the data sheet. So here we are on the data sheet, and we're going to scroll down a little bit more to where it gets interesting, because we want to know. Remember I said that we were going to do a DC isolator installed outside in direct sunlight. So I better go down to the ratings for different temperature categories. Here we go. So you can see on the left-hand side, we've got a bunch of different rated thermal currents. And so there's the unenclosed at 40 degrees in the shade, ambient. There's 40 degrees in the shade with a dedicated enclosure. But remember, we're actually in direct sunlight, so that neither of those are any good. There's the 40 degrees without solar effects. Now that means that it's in a location that could be impinged by sunlight. No, we're on a roof. Even with a shroud, we'll still be exposed to some sunlight at some point. So we really need to use the last maximum current rating, which is a solar current rating for outdoors at 60 degrees Celsius. It's still shaded, but it's exposed to solar effects because the shroud doesn't fully shade it all of the day. In fact, there's a bit of heat transmission from the shroud too. And it's rated to IP66 no water NW. So 29 amps is the maximum current. So we go and check our design and jump back to our design now. And we had a maximum current of 13.5 amps, so we can do it. This disconnector is rated for 29 amps indirect on a roof outside in direct sunlight. So 13.5 is less than 29 amps, so great. So that's 29 amps, and that's a tick. It's suitable for this maximum current, so that's good. Okay, next step. Number of poles switched under normal operation. Now, remember I started off today talking about separated and non-separated inverters, and in fact I'll go back to the non-separated inverter for a second and show you. Now, I've drawn a fault condition where the current's only flowing through one conductor and the switched poles of one conductor, but in practice, this is a fault condition, not normal operating conditions. So under normal operating conditions, I'm going to rub this out. So it's not a fault. We just want to be able to switch it off. So we get rid of this fault altogether. And when it's working, we want to be able to switch it. And how many poles will be interrupting the current, because the current will be actually flowing like this through the inverter and back the other way. So we actually have a bidirectional current flow. That means both conductors are switching the current at the same time. It's a requirement that they interrupt simultaneously the current. So we've actually, in this example, got two switched poles, but if we go and look at the data sheet for the ZJBeny, it actually has 4 switched poles. And if I go down to that, here we go. So it's a 4-pole device. Not too dissimilar in terms of its configuration, but then something like half of one of these. Hang on, I'm just going to bring that one up. So that's an 8-pole switch disconnector or isolator. If I had half of that, I'd have got 4 switched poles. So 1, 2, 3, 4, and this one's an 8, so it's got another 1, 2, 3, 4. So on each side, I'm in this case switching 4 series poles, but the ZJBeny that we're looking at, the data sheet, which I'll go back to, has 4 poles in series. So under normal operation, it can interrupt 4 switched poles, and therefore at our 597 volts, it's suitable for 32 amps. Look at that, 32 amps. So 32 amps is ample for our requirement. We only need 13.5. So it can certainly do a normal operation switch. So we're getting there, and the last step really is to look at what's going to happen under a fault condition, and that's when we are switching because of a transformerless inverter. So if I go back to this diagram here, so now we need to know, so I'm going to put 4 poles here, the answer is 4. And the number of poles switched under fault condition, only half of the poles will switch, the positive half or the negative half, depending on which side the fault's on. So that means we've got a 2-pole rating. So 2 poles will be switched under a fault condition, and therefore I need to go back to the data sheet. I hope you're not getting dizzy with all this switching back and forth. Excuse the pun. And the 2-pole rating at 600 volts is 32 amps, great, but it's the I make, I break that we use. So the I make, I break is for fault conditions. That's why it's a kind of new thing. It's always been a part of that test in 60947.3, but now we're using it to acknowledge that under fault conditions, you will not be doing this switch like 100 times or 1,000 times. You'll do it once probably, and then replace the faulty inverter. So we're allowing for quite a high interruption of current, which in practical terms, is actually starting to degrade the switch mechanism. So it can't do it many times, but it can interrupt at up to 128 amps. So that's heaps. It's well above our 13.5 that we required. So all's good. This switch disconnector is just excellent for our particular application. Now, I did this whole thing around looking at a domestic installation, but of course, once you start climbing up into those higher voltages, that's where it gets a bit more tricky, and you need to be a bit more discerning in the selection of your isolator. So I'm just jumping over to see if any comments have come in yet. So I'm looking over it in YouTube. Nothing there. Maybe someone might say hi just to let me know I'm actually getting the right feed. And I'm looking over in Facebook land. Let's have a look at Facebook. See if I've got anything going on over there. On the Smart Energy Lab Facebook page. And there we go. Looking for some thumbs up. You know the story. If you're enjoying the live, give me a thumbs up. And if you want more of this content to pop up in your feed, don't forget to press the subscribe button in YouTube land. So still just checking out the questions here. Great. All right, there we go. Thanks. I got a few highs there from Adam, from Andrew, from Rob. Yay. Good to know that's working. And it's jumping over to YouTube, see if there's anything in there. There's a silly idea. Yeah, I think we should ban rooftop isolators. Yeah, you never know what Santa might bring you for Christmas. So just keep your eyes out for the next edition of 5033. It's going to go to public comment probably December, I'm thinking. I'm actually on the committee, so that's what I've been told. So I think we've got the public comment coming out pretty soon. And you never know what Santa might bring you for Christmas in his standards bag. So there might be some good news for a change. But yeah, you'll have to wait and see. And just for those who are not familiar with how standard is developed, there's a committee, in this case EL42, made up of stakeholders, like 40-something stakeholders involved, and we collectively write the standard. but of course it then has to be approved by the community who use it, so that's the public comment phase, and that means basically anyone. And those public comments are reviewed, and so the review process is pretty important. That's where we can, be told we've missed out something really important, or there's, typos, etc. So there's some great people out there who read these standards cover to cover and say, you forgot a full stop on page 33. Yeah. Thanks very much. That's really good proofreading. But often it's we strongly object because of, and you give a good reason for it. You don't just say, oh, it sucks. You've got to actually give a good reason. So, and sometimes it's really encouraging changes with fixed problems, and that happens when you've got a standard like 5033, which has been around since 2007, I think, or 2005, first edition. It's had 3 full revisions and 2 amendments, and so it's getting better and better and better. But then there's always challenges. This new tech comes along, new products, and somehow they sometimes break our standard, really come up with solutions that might be great, but the standard might disadvantage them. Now I'm just double checking, see if there's any comments that I've missed. Okay. All right, well, I think it's probably a wrap then. So this is a short and sweet one. I did promise that I'd be getting back to doing interviews, but I haven't got to it yet. It's been a bit of a busy week and a busy weekend, actually, with children's parties here at the Smart Energy Lab, and which is also my home. But yeah, I do hope to get back to doing interviews on Sundays. So anyway, until next Sunday, 2 p.m, Toolbox Tech Talk here, same time, same place. Not sure what I'll be doing then, but no doubt promote it. So yeah, thanks for watching, everyone. See ya.